All right, so thanks for coming out to this talk. It's titled Cozmo, Animation Pipeline for a Physical Robot. And it's probably not very standard for GDC, because it's not really about a video game in a strict sense of word. However, it's certainly game-related. It's going to be about a physical robot, Cozmo. This is him. And we will share with you some challenges we faced and the lessons we learned when applying game and animation pipeline principles to robotics. To tell you a little bit about ourselves, this, by the way, was recorded with Cozmo's camera, so he has vision recognition and the camera built into him, and this is kind of how he sees the world. So my name is Daria, and I'm an animation tools engineer at Anki. I come from a feature animation background and have previously worked at the stop-motion company Leica, where I started as a CG rigger and then worked as a TD, writing tools for CG animation and 3D printing pipeline. My job at Anki as a tools engineer is somewhat similar to a pipeline TD role in feature animation. I create tools that automate work of the animation team, as well as tools for transferring data from CG software to a physical robot. The process will be expanding more as the talk progresses.
And my name is Molly Jameson. I'm a software engineer at Anki. I've been there for about a year and a half. I previously worked as a gameplay programmer at places like Insomniac Games on titles like Ratchet & Clank and Resistance 3, and at Big Fish Games on the casual and web space. So this is the first company I've worked in that has a physical component. So I'm going to talk about how transferring working on a physical device is different from working with in a pure virtual environment in traditional gaming.
All right, so there are many aspects of Cozmo development we could explore, but this talk will focus mainly on animation tools pipeline, as well as engine flow and unexpected problems that aren't generally encountered when working in a virtual world. We will give you an overview of what Cozmo is and why we're using custom animations in order to convey his personality. We'll talk about how we're exporting animation to a physical robot from a CG software, which in our case is Autodesk Maya, and how our workflow differs from a typical animation or games workflow. We'll describe architectural layers of Cozmo and talk about the relation between gameplay, engine, firmware, and hardware. We'll also talk about how real-world uncertainty comes into play when applying animations to a physical robot. We'll describe the QA process in Cozmo and our experience with the robotics pipeline coming from animation and games industry.
So to give you some background information on Anki as a company, we're a robotics and AI startup based in San Francisco. Our initial claim to fame was when Tim Cook introduced us on stage at WWDC in 2003 to demo Anki Drive, a battle racing game that allows players to race AI-powered cars around a printed track using their handheld device. In 2015, we took the learnings from Drive and launched Anki Overdrive. These products gave us a good foundation on how to build consumer robotics in the entertainment space, but all while that was going on, the company had hopes to build a robotic character, which eventually turned out to be Cozmo. The idea had been around since 2011, but we really started production on this newer, more ambitious project in 2013. In October of last year, we finally launched Cozmo, a companion robot also described in the Toys to Life genre. So what is Cozmo? The best way to explain Cozmo is just to see how people interact with them. So here's a short video from one of our play tests that I'll talk about afterwards.
You're grounded.
So in essence, Cozmo is like a robot pet, a real robot character you interact with, and he can recognize faces and interact with the real world around him. Cozmo can make eye contact with a specific person and interact with people directly by pouncing on motion he sees or bringing them one of his cubes if he wants to play a game. In addition to the more free-roaming capabilities, Cozmo also plays specific rule-based games. So in this example, Quick Tap, you need to beat him by tapping the cubes when they're the same color faster than Cozmo does. Or we have another game, Memory Match, where the cubes will light up in specific patterns, and you need to tap a pattern longer as it gets longer and longer, and Cozmo will try and compete with you. Since everybody loves camera shake, this was also me camera shaking, because it's hard to tap a cube and film yourself at the same time. So this is real-life camera shake, more video games than the real world. So we use these games to showcase Cozmo's personality even more. So when he wins and loses, you can see his mood is affected in the whole metagame, and players can really focus on Cozmo himself. Like, we use the phone as like an auxiliary display for a scoreboard, but really players should be focused on Cozmo himself while this is all going on. So yeah, like, we think we were pretty successful in making people attached to Cozmo, although I would amend Kotaku's comments, my cats do in fact try and eat Cozmo on a regular basis. But a lot of our success in making a believable robot pet comes from Cozmo's unique animations.
All right, so you may ask, why did we choose to apply custom animations to Cozmo in the first place? And what's so special about the way we do it? So people have been building robots in order to automate different aspects of their lives for a long time. Here, for example, is an automated way of assembling cars or creating laboratory tests. The most important thing for a robot built for something like car assembly is to perform its task in the most successful way. So if, let's say, it needs to take a car part and put it in some place, we need to ensure that it does place that part where it needs to go and doesn't mess up along the way. So all our manufacturing process would depend on that. And to ensure that the robot succeeds in performing its task, it needs to move with a consistent speed and make only the movements necessary to accomplish what it needs to do. However, we are not building a robot for task automation, so the challenges we face are quite different. Cozmo's purpose is to be a fun companion, so we focus on his personality and entertainment value. Unlike the previously described robots, the successful completion of the task is not as important for us as creating an engaging experience. To put that in perspective, here is an example of a robot from Willow Garage. Its task is to get a bottle of beer from the fridge, and it does that with the least possible actions. It's not going to go back in the opposite direction or slow down for no reason. And that's partially why its motions look unnatural to the human eye. So in real life, we are not used to seeing creatures move with a consistent speed and have linear motions. It's the difference in timing that makes things more interesting to look at. So here, Cozmo is bouncing on a cube with no animation applied. And you can see how much less interesting and appealing his movement is. In fact, it starts resembling more the way a typical conveyor robot would move. So our challenge was to make Cozmo's motions look more natural and have them to convey his character and personality. So sort of get from that to what you saw previously. And that hasn't really been achieved in robotics on the level that we are trying to do it. However, it has been a solved problem in other mediums. So here, this is a commercial from the early days of CG animation. And we can actually see the same challenges that we are trying to solve. So these characters' movements look unnatural and somewhat funny to us now, especially if we compare it to the CG animation of the present. Like, if you pick any CG film or game that has come out like in the last 10 years or so, you can see that CG animation has come a long way. And that was achieved by applying an artistic input to CG animation and by giving a better creative control and creative freedom to animators, who in turn were able to have characters display personality and appear more realistic. So similarly, we chose to apply custom animation to Cozmo so that an animator can make creative decisions on Cozmo's acting choices. Here is the video with the same pouncing on the cube animation as shown earlier, but this time with animation by Lia Suelo. And you can see how much more personality is now being conveyed through Cozmo's movements. So this illusion of him being alive is something that we strive for in order to make people interact with Cozmo as a pet rather than a robot. So unlike with something like a conveyor robot, We don't care if Cozmo is doing extra actions or changing speed, as long as he's interesting to look at. So once the decision was made to apply custom animations to Cozmo, we were faced with the challenge: how to give animators creative control and the ability to actually animate Cozmo. We chose Autodesk Maya for animation because it's a mature tool that meets all of our needs and minimizes the learning curve for animators with previous Maya experience. We're specifying Cozmo's motions using data stored in the form of a JSON file. Each JSON node specifies the values of a specific Cozmo part, as well as when its motion gets triggered. We control Cozmo's head and lift, which we can raise up and down, wheels, which he uses to move forward and back, backpack lights that change color and intensity, his face, which is an LED screen, and the speaker, which is here on top of his head. We had to make Cozmo's model and rig represent the way the robot looks in the real world. So the controllers he has in Maya resemble the same parts of the robot that we can control on the actual physical character. This way, animators can animate the robot completely in Maya, as they would a character in a CG film, and then transfer that animation to a physical robot. Values on the controllers adhere to the values in the robot itself. So as animators key those controllers, we can analyze and export their values. We animate each track separately, but in parallel. So each track has its own set of keyframes that are serially played on the robot, but the tracks themselves are processed in parallel, allowing, for example, how in this case, the head and the lift to move simultaneously. And to give you a breakdown of how we do it, here is an example of a JSON file in form of a single node. A file like this would make Cozmo move his head from its previous position to 45 degrees up. And it will take 1,650 milliseconds, which is 50 frames, to complete that transition with a linear interpolation. And here's how that looks in Maya. We can add another node responsible for the same Cozmo's part. Its motion is triggered when the first one ends. Robot interpolates the movement from the previous position to the new one, which is why we don't need to specify the start position in each node. As a result, Cozmo moves his head from neutral 0 degrees up to 45, and then back to 0. In this case, lift movement is added to the exported file. And you can see no structure for the lift is the same as for the head. And this example shows how two can move in parallel. So you see that he first moved the lift up, then the head, but their timing is different. In case of the head and lift, the values are absolute. For example, a keyframe that sets the head angled to 20 degrees will result the head rotate upwards by 20 degrees, regardless of where the previous keyframe positioned the head. That, however, is not always the case. So with Cozmo's body motion, for example, we're specifying his speed rather than position he needs to end up at. And that's different from behavior we see happening in Maya. So in CG animation, in order to move the character, we change the position and key it where the character starts movement and where it needs to end up at, so that the two positions can be interpolated between. But what we need to export is Cozmo's speed. So how do we deal with Cozmo's movement? There are 3 different kinds of movement that Cozmo can make. Moving forward is the most simple one, where he moves from one point to another in a straight line. Another one is turning in place, that this video starts with, and the arc turn at the end of the video, which is the same as turn in place, but with radius applied. We are separating the movement that way because it best resembles the movement model of the physical robot. So when 2 wheels move at the same speed, robot moves forward. When one wheel moves slower than the other, robot moves in an arc. And when one wheel moves the opposite to the other, the robot makes a point turn. So the robot's true motion is complicated because of his treads and the friction properties of the surface he's on. A full model of this would be difficult or impossible to work with, so we simplify it to this differential drive model, where the robot has a center point and 2 wheels. And you can look up the information on differential drive equation if you would like. There's a lot of information about it online. But here's sort of a simple formula. And omega, in this case, is the rotation rate of the robot. R is the radius of the turn he's making. And L is this distance between his 2 wheels. So then you see it equals to V, which is the speed of the robot, and VR, in this case, is the speed of his right wheel, and VL is the speed of his left wheel. So in order to set robot's movement, we ultimately need to set the speed of his wheels, which is being calculated based on that equation. So if we know the distance between the wheels, which we do, rotation rate of the robot, and the radius at which Cozmo travels, we can find what his wheel speed will be. So due to that, the main 2 things that we need to export are radius and speed. And from speed, we can calculate the rotation rate. And from looking at the data we export, you can see that the 2 things we export when it comes to movement are indeed radius, here, and speed, which is here. And if the robot doesn't move in an arc, we specify the type of movement he is doing in the radius parameter. So if there is a radius value set, the arc turn happens. Turn in place would mean that there was no radius applied to the turn, and straight means that robot is moving in a straight line. And a JSON file, as the one you see, would make the robot do a turn in place, a straight movement, and a turn in the arc. So the same video. Due to the way we export data, Cozmo's main movement controller has 3 parameters: radius, forward, and turn. In CG animation, turn is usually achieved as a combination of translation and rotation. In our case, we set the constant radius and animate the turn parameter, which is Cozmo's rotation. So turn and forward cannot have values at the same time, because Cozmo either turns or moves straight. If Cozmo makes a turn after a straight movement, his position gets reset to be 0, and then turn can be animated. The way we deal with audio is also quite unique. And this, by the way, is a picture of Ben, our audio designer. Unlike games or film, our site designers work closely with animators and set keyframes in Maya based on where audio events need to trigger. In feature films, sound effects are usually being created long after the animation is done. And our pipeline is different in that regard. We set the time where the audio event starts playing in the same JSON file where we specify where different Cozmo parts should start moving. And in order to sync robot's audio with the rest of the animation, Audio Designer places keyframes in the Maya scene itself. So this close collaboration between audio design and animation allows animators to make acting choices based on sound effects and change their animation even after audio events have been added. So to summarize, even though our workflow is similar to that of a feature film, there were certain aspects we had to adjust to due to real-world constraints. And here are only some of the examples. Movement of the certain parts is limited to how much they can move on a physical robot. In feature film, as well as in games, animators can often push the rig to do actions that would be impossible in the real world for a subtle extra effect. So, for example, they can choose to bend a solid object or have parts of the character intersect. In our case, we can't do that. If the robot can move the head 45 degrees up, that will be the highest it can go in the rig. Animators won't be able to push the head to go any further. Due to the relative versus absolute values, as well as robot's single axle structure, we couldn't key robot's position to animate him move. Instead, we had to create a CG rig with attributes for forward movement, turn, and radius, and calculate Cozmo's wheel speed after the export. Our audio events have to be set together with the animation and exported from the Maya scene for timing purposes. Now, at the same time, sometimes we get certain interesting results from animating a physical robot. And these happy accidents are usually being discovered by the animators. This iconic example is when Cozmo recovers from being placed in his head. This was a motion our animators came up with, and our hardware team was legitimately surprised that this was possible. So this is a more subtle example, which is easy to miss. So please pay attention to this animation, and when you do, look at the lift and the way the lift raises up in the beginning of this video. You can see that Cozmo brings his lift up by a very slight amount and leads with his right side. So Cozmo's motor is positioned on one side of the lift. So when it's being raised up, one side goes up slightly sooner than the other one. And you would often not even notice this effect when looking at Cozmo, but it is the kind of effect that the user feels rather than notices. And animators can use it to their advantage. For example, in the case when Cozmo is making a turn, or when it needs to do like a subtle lift movement to make him look alive. Now, usually in robotics, iteration cycles are fairly slow, and engineers can work in a simulation environment for multiple days before they would see the results on the robot. For us, fast iterations were crucial, and we built our architecture accordingly. We made sure that we have an ability to play our exported animation in Weebots, the simulation software we use, and have an easy way of seeing what it would look like on a robot. We speeded up the process even further and created a preview tool that allows to play animation on the robot from Maya itself without having to change software. Since the animation on the robot and in Maya can be so different due to real-world constraints, it was important for us to give animators an ability to see their changes as soon as possible. And so this is how the final result looks like. This is how Cozmo's animation looks like in Maya. And this is the same animation in the real world. So now that you know how we create and test our animations on Cozmo, it's important to talk about where it exists in the context of a game. And this is where Molly comes in.
So to understand how the animations are played in the game, we need to take a step back and look at Cozmo layers as a whole. So the important thing about Cozmo is that his brain is on the smart device, not on the robot itself. The first thing the customer is told to do when they're unboxing their Cozmo is to download the app onto their phone or tablet. So everything the robot does is sent to him in real time as an action or an animation. So in a lot of ways, it's like running a server and a client in a game. So part of why Anki thinks this is a really good time for these types of connected toys is because parts are getting cheaper and everyone has a smart device now that we can keep upgrading and keep sending updates to, like the traditional games as a service model. Going through this, on the top layer, we have our gameplay and UI layer that runs on the device. Think of this as like Cozmo the product. It's responsible for like all the game logic, the UI you actually see on the phone, the game rule sets, and Cozmo's skill level with respect to the player and how he actually like plays with him inside those rules. We can swap that out with a SDK that we give to hobby roboticists that sort of replaces the whole game layer. The SDK is being used at several universities right now, including Carnegie Mellon Robotics Institute, since Cozmo is a lower-priced robot than most other academic robots, and they can use it to create all sorts of user-generated content to run on the robot and just display whatever they want or combine it with any other Python APIs that they want to combine with Cozmo. So it's a really cool way of exploring it. The main workhorse of Cozmo is on the engine layer, which is in C++. So it's responsible for like reading in all the assets and configs, including animation, decompressing them, Wi-Fi connectivity to the robot, all path planning, AI behaviors and free play, and all his goals. computer vision, like just image processing, faces, markers, and motion sensing, and everything in the computer vision bucket. Streaming data down to the robot, all the native OS interfaces, hence the Objective-C in Java on the chart, like backgrounding permissions, crash reporting, and all that good stuff, and keeping track of the world state. So Cozmo himself is an access point, which is actually a really interesting point about Cozmo. So you actually disconnect from your router and connect to Cozmo as if he were a router. So it helps a lot with privacy, and it helps a lot with latency. It's a pretty unique architecture that way. I'm not going to talk a ton about hardware in this talk, but it's really important. We went through about 45 iterations of mechanical designs of Cozmo before we got really far into software design at all. He's about 300 plus parts inside the robot itself, so the hardware design was obviously really important. But that just sort of controls like the actual mechanical limitations of Cozmo. The firmware is a light C layer we have running on 3 custom processors inside the robot himself, so it's responsible for streaming data back to engine to tell the engine about its robot state, running the actual motors and LEDs on the lift and the speaker, and interpolating keyframes over a certain duration of time. So what that looks like in practice generally is like the gameplay layer will trigger some game event that has an animation associated with it. You can see here we just use enums for this to play an actual animation group, which is an extra abstraction layer that lets animations have multiple different animation types play within a group that can have specific rules, like have certain animations on a cooldown or only play certain animations when Cozmo is in a mood, so that the animations appear more varied. Once the gameplay request animation is made, that's sent down to our engine layer. So the next tick, engine will start to buffer the audio. It takes about 230 milliseconds of audio data we want to get before we start streaming it down to the robot's animation buffer. This gives us a large enough head start where we won't hear any stuttering if a frame rate spike occurs later or if there's some other delay. Currently, we're using WIs for Cozmo's audio, but it really could be anything that allows real-time pitch variation. So when an animation is exported, we actually don't know how long the audio is going to last, because what WIs can modify that in real time. So once we have enough audio stored up, we start to stream that down into the robot. The robot itself is, like I say, is running custom processors, so it doesn't have a whole lot of memory to store it. We can store about 250 milliseconds of data on the robot at any one time before it needs to stream back more data from the phone. So the engine will just keep sending data to fill the robot's buffer as much as it can take. It's about 30 milliseconds of lag time round trip, so communication on this thread is a really high priority. Otherwise, you'll hear or see Cozmo stutter, which is a jarring experience. So once that's down onto the robot itself, it'll take all the different keyframes and interpolate between them, sending them to the correct motor, or in the case of a face, updating the screen, the OLED display to whatever the new image is. So this is what the final product looks like after it's been going through all those steps. When it's completed an animation, it'll either call the callback that you sent in, or it'll start just playing idles again and waiting for the next behavior command that gets sent to it from engine. So all that was kind of the ideal, but as we know in the real world, things are never perfect. So this is sort of some of the lessons learned and issues we ran into. I'm going to go over 4 major design and implementation challenges we ran into when trying to bring a robot to life. So the first thing is we can't really control where people play. We'd often want Cozmo to move a certain distance over a certain amount of time. So as it turns out, adult developers like to play sitting on their desks, but kids really like to play on the carpet or sandbox, and obviously all those have really different friction properties. And when animators exported, they could only control what speed they thought the robot was going at. So in this video, this is Cozmo going at what he thinks is top speed in all circumstances, but obviously it takes a bit of time. So to fix this, we just need to figure out where Cozmo is in the world, and if we need him to end in this specific position, end at that position. But how do we know where Cozmo is in the world? So this problem of where is the robot can be generalized to the field of robot localization, and this is going to be a very high-level view of a large field of robotics study. Also in robotics, localization means where the robot is local to other objects in the world. It doesn't mean translating to other languages, which is another large part of confusion when games people talk to robotics people, as I learned. So to know where Cozmo is in the world, we need to look at how Cozmo sees the world. So Cozmo can process the world around him through a series of input sensors. So on the bottom of Cozmo in this picture, you see is this cliff sensor, which is an IR sensor that he sends from the bottom, from like underneath him, that they can use to tell if he's currently driving off an edge or if he's hovering off an edge, so he doesn't appear to like go off tables or anything. He also has an IMU inside his head that consists of an accelerometer and a gyro, so he can feel if he's been picked up or if he's being rotated and sense his axis that way. He also has wheel encoders, which sort of work like an odometer, so we can tell how often his wheels have turned, which will give him an approximation about how far he's traveled. And most importantly, he's got a camera, which is where a human would think his mouth is. And that he uses for face detection and any sort of motion detection, and also for the cubes that you saw earlier. So he also has his charger contact, so we can actually tell when he's being charged, which is actually kind of an important sensor for how your robot gets power. So on top of that, Cozmo also comes with these cubes that we were sort of alluding to before. So the 3 blocks also have custom hardware inside of them. In addition to that, they're also globally unique, meaning they're all different from each other. Meaning each of these 3 cubes look unique to each Cozmo. They also have 4 LEDs on them we can use to communicate with the player, an accelerometer inside each cube so we can tell their orientation in the world, and also if they're moved. And they have a radio inside them they can use to connect to Cozmo to show their state. So in the fiction, he loves these blocks. They're sort of like his own toys, and you can see from the form factor, it's implied he can sort of pick them up and roll them around. We even use the lights on them to communicate that Cozmo has some sort of intent to interact with one of these blocks. So this is a picture of the cubes unrolled. They have distinct fiducials on each side. They're made to look similar to humans, but obviously Cozmo's vision algorithm has been trained to recognize each side, so he knows their specific orientation and which side he's looking at. So one of the ways Cozmo reasons about his location in the world is where he is relative to these markers. You can see on the right, he's sort of built his simulation of what he thinks the world looks like based on that image. And if he happened to turn away, we sense if a cube is moved based on its accelerometer dirtying, so then Cozmo won't try and reposition based on that cube. So on a high level, most minigames are just him driving up to some cube where he knows where it is and interacting with it in some way. So unlike in video games, we can't build our nav at build time in the level because everyone is going to be different. So we need to do simultaneous localization and mapping, otherwise known as SLAM. So we gather all the data from the sensors, so the cliffs and the IR sensor and the map and the camera, and sort of put them together. So here's a video of Cozmo building a quad tree of like known good areas to drive over. And so anytime he sees a cube, he can be pretty sure there's no obstacle between him and that cube, because otherwise he wouldn't be able to see what was behind that obstacle. If he's ever picked up, he knows to invalidate this map that he's building and start over again. But if he sees a block again, he can go back and be like, oh, I know where I was relative to this. So he stores his old maps that he has too, if the blocks themselves haven't moved. The actual planner is a lattice planner we use for pathing. So in a more detailed example, this is a bit more debug data on it. Here in red, like, he knows that the cubes themselves are an obstacle that he shouldn't drive through, so he knows he needs to path around that. In the light green, this is him seeing that he can actually see a cube, so that means there's probably not an obstacle between him and that cube, so it's probably a safe area to drive up on, but there might be like a big hole, or it might be on another table, so he's not entirely sure. The green areas are places he's driven, so he knows those are safe areas to path through, and the area in black is an area that he knows is a cliff, so he knows to avoid it and not to triumph over that area. So in summary, like the way we know where Cozmo is in the world, it's just by interacting with all those blocks and fixing it if he's been delocalized and trying to build his map again if you really can't see any markers from where he was before. So all that combined, we can make Cozmo end up in a specific location that we want him to without having to author it into the animations themselves. So another challenge is making similar content work in different situations. So authored animations need to be flexible to play in different contexts. So here's an example of our first pass at trying to make Cozmo drive while holding a cube. So you'll see he's just driving, and then that was his drive animation. So we found out early on the animators would do things like keyframe the lift being down, because it would look weird if you started walking around like this. But that's what we wanted when he was holding a cube. So in this case, Cozmo started to drive, but then the animation of driving made his lift go down. And the desired behavior was like, oh, we actually want him to be holding it, but we didn't want to double the animations that we needed to create. So instead, what we did was, to prevent these types of problems, we sort of prioritized behaviors controlling certain tracks, most notably the lift in the head, so that we could reuse the same animations and like facial features and sounds while still using it in those contexts. So here on the left is a video of Cozmo's normal cliff reaction, and you can see he sort of does this surprised lift motion. And if he does that while holding a cube, it's more locked into place now. So he still does the same like surprise with his head, but he doesn't suddenly throw his cube, which was obviously not the desired behavior. So that let us reuse animations in multiple contexts and sort of just prioritize what we wanted to show off. So challenge 3. So one of the other main issues that we ran into repeatedly was recovering when actions unexpectedly failed. So in this example, this is an example of Cozmo successfully rolling a cube, which is one of the main activities he does. So he goes up to it and he drives up to it, and that's really cool. But you can tell there was like an 8-second pause there where someone can break in and just move the cube. So by far the biggest thing getting used to when coming from traditional games that came up time and time again was that sometimes things are just not where you left them, and Cozmo failed to complete some interaction. I've worked on MMOs where this is like an edge case, and you just kick people back to the lobby and tell them there's a desync error, and the sim doesn't match the real world, but that's really not something we can do. We can't just tell people their world doesn't match our sim. So it actually is no longer an edge case and is a main case that happens quite frequently. So here again, some evil human me is moving the cube while Cozmo is trying to interact with it. And so the trick here is that Cozmo will play like a frustrated animation and search for the cube, and most importantly, retry the behavior as part of our goal, as part of the design of every behavior we had Cozmo do, whether he's rolling a cube or stacking a cube. So our philosophy is we aim for a really high success rate with the robot, but we need to provide a graceful failure if anything's happened. So most of the interaction behavior were designed in such a way that there was a set time for a success or animation failure could play that could be read and easily understood by people, and then the behavior can retry. We trigger these failure cases, and it added a lot of variety and made the behavior robust enough to handle several retries. So when designing it, we had to weigh accuracy versus speed. In practice, in mini games, it's just a game design trade-off of how accurate Cozmo needed to be and if it was worth the time it would take to verify that something was still there. And Cozmo can move pretty fast when he's not actually trying to verify something. It's part of the reason he's so small is because big things can fall on things and be kind of dangerous. And also being small helps him move fast, but we have to kind of slow him down when we need him to actually look at something and verify that it still existed. But it helps a lot in Cozmo seeming smart because he realizes something has gone wrong and he can interact with it. So it's really kind of a architectural thing to prioritize of like make sure you consider your error states early and often. So another big problem that's familiar in video games but slightly different in this context is directing the user's focus. So we have a problem because we have two things we need the user to pay attention to sometimes. So we have a phone screen and we have a robot. In other games I've worked on, you can pause or flash or highlight or drift some particles somewhere, and people will hopefully see what area of the screen you want them to look at. But we don't even know where the robot is in location in comparison to the device. Like, some people completely put their phone away in the case of this, and sometimes most of the time we want people to focus on the robot, but sometimes we need them to look at instructions or see their score or something, and they need to look back at the camera, and we just don't know where they're looking. So as a solution to this, if we need players to look at Cozmo, here's an example of him bringing you a cube because he wants to play a game with you. This is a bit sped up. So after he's brought you the cube, he sort of looks at you and gives you this, "Hey mom, look at this thing I can do," and is very proud of himself and will track your face until you do something and interact with them. It's a really good example of like the power of eye contact if we need players to hopefully look over at the robot. And when we need players to look at the app, we sort of quiet Cozmo and make sure that the app made some sort of noise. It was really nice because our audio designers designed audio for both the robot and the app itself, so we could sort of make them interact with each other. Of like, Cozmo could like not make noise if he's playing a set of animations, and then the app could also like make noise to be like, look over here, which was a nice way to coordinate what events we wanted players to care about. So those were the main things. Ship it. But first, QA it. So we ran Cozmo through a suite of automated testing. So our build service ran scripts to verify animations still existed every time they were checked in. Other integration tests ran on our simulator here on our build service, check for like logical build errors and regression tests. For instance, like we had animations that needed Cozmo to end in a certain state or pose, like he needs to be looking down to look at cubes, so we could verify nothing had happened there, or verify that animation still existed that we thought existed, so there wasn't accidental changes of really important animations, or just verify that behaviors still worked in general. So what I took away from this is that programmers from robotics backgrounds are far more serious about writing automated tests than games programmers ever were. Something about being from a field where they work on life-threatening projects is really motivating to make sure their code still works. So Cozmo was the most heavily tested piece of software I've worked on in 10 years in the games industry, so that's really impressive if you want to learn how to write good automated tests for your stuff. But as usual, there's a lot of stuff automation can't see when something just looks wrong, so for that we need manual testing. It's manual. There's a human in Jira in this picture, and one of our testers, Rachel, and her many Cozmos. So even when we stopped having prototype robots and started getting mass-produced robots from the factory, they can still be sort of special snowflakes of robots and be slightly different from one robot to the next. So we received vastly different player input for gameplay based on surfaces, lighting, temperature, and also just tuning the robot itself was sometimes different. So we were prepared for subtle differences to occur between robots. So one of the main examples of just gameplay differences we ran into is, like this just shows really well, is lighting conditions on the cubes themselves. So this is cube visibility, especially since the cubes have LEDs on top of them, which in up to a black and white camera sometimes sort of bleed into the borders of the cubes, making them hard for Cozmo to see. Turned out to be a big problem and need to be tuned in multiple conditions. So in addition to that, vision processing also changed a lot per smartphone device, since low-end devices could drop frames as you're used to seeing on any sort of low-end to high-end to min-spec to high-end device. So which makes it harder for Cozmo to see, because obviously the more things are moving, the more motion blur occurs, the less likely it is to be a crisp image. In addition to that, Cozmo's camera is on his head, so he could be moving in addition to the cubes moving, which compounds upon the problem. So a lot of the initial images we tuned based on what Cozmo could see or not. And so all these initial images were captured by our normal test team, but then they were brought back into our automated tests to make sure they still worked as we fiddled with the auto exposure of the camera itself to try and make it work. But ultimately, one of the things you need to do is just message to your users really clearly when they're in what you think is a bad state. Like if all Cozmo is seeing is black, we sort of just suggest to the user that maybe they need to turn on some lights. We also do this if a driving behavior keeps failing, like maybe suggest to them they need to move to a cleaner table-like environment where that doesn't happen. So yeah, that's an example of like one of the test plans we had for Cozmo. But as usual, when you're testing, sometimes the key is just to get creative. This is the state-of-the-art robotics testing for vision processing. This is me needing to test multiple face recognitions when developing locally. So robots are the future, everybody. So this is our unique sort of combination of the two testing. This is the final factory test that Cozmo runs through. So this is after he's been completely put together along the assembly line. He has to run through this test with an operator watching. So you can see this is testing his camera calibration on the checkerboard there, that his cliff sensor properly went off on there, and finally that he can pick up a cube completely. So this is for high quality control. Only after he can get past this entire robot obstacle course is he put in a box and shipped to a customer. So in conclusion, some final thoughts about testing. So fundamentally, hardware testing needs to be finalized long before software even starts. In our case, it was about a year. And QA should have access to ways to test the robot itself without software sort of getting in the way. And features need to be tested across multiple robots, multiple devices, and multiple environments for a very nasty test matrix, but it needs to happen because there's lots of things that can affect you, from like humidity to all these other conditions that don't replicate in San Francisco, but are very important if you ship nationwide. Yeah. So there's humidity, temperature, and whenever you drop the robot, you can claim you're testing it, which is a pretty convenient excuse. In addition to that, there's a lot of regulatory testing that I didn't have to deal with in video games that I deal with here. So like Wi-Fi interference and children's products considerations that you're not crushing fingers or anything like that, or have a certain amount of lead, all that things in your product comes up. So it's much more strict than any TRCs I had to deal with, since these are actual governments you're working with and not companies. So yeah, thanks to the team who helped us out a lot with this presentation. And questions?
We also want to specify in thanks that it's really like it's a huge collaboration between a lot of people. And so even though, so for example, the tools team is very small, it's actually just 2 people. And our animation team is actually pretty small comparing to other projects. And 3 of our animators are here, so you can actually talk to them. Yeah, but yeah, we'll be happy to answer anything you have questions about.
I noticed one of the movements, he would pounce on a box and his front wheels would lift up. Were there any like physical interactions that required several layers of testing to make sure that the animations didn't throw off his positioning?
Yes. Yeah, and in addition to that, there's a lot of actual subtle things where Cozmo would then suddenly think he had been picked up because he had lifted himself up. So we sort of had to gate that a lot of like, no, he's playing an animation that is meant to do that, so that's okay. Because all he has is a cliff sensor, so he'd pick himself up and then he'd be like, oh no, I've been picked up. So those animations tend to need some code help to gate cases like that. But yeah, one of the convenient things about him having treads like that is when you turn his treads, he'll still move, like he can still get himself back down, hopefully, if he's picked himself up in a cube. We have some behaviors actually, like pop a wheelie is like an intentional behavior where he'll go up to a cube and then he'll lift himself up and it's always a big hit. And then conveniently, he has that bug behavior where he'll just, it looks like he's moved, like that Daria showed in that movie where it looks like he's trying to get himself down with his own lift, but actually it's his wheels that are getting him down at that point. It's the classic redirection where his wheels will just turn him down. So there's lots of ways he can try and correct himself if that does happen.
Thanks to presentation. And I came from Japan. And do you have a plan to this robot released to Japan?
We can't talk about future roadmap stuff.
Thank you.
I was coached.
Hey there. So I noticed that you were kind of doing like pathfinding, kind of like SLAM, stuff like that. And I was wondering if you were doing more kind of like dynamic collision avoidance. So if it seemed like if you have a static map that you do, but what if like the blocks are moving around, or potentially you didn't show this, but potentially if you have like 2 or 3 Cozmos like moving around, then you want to maybe just like avoid something that's moving.
So currently we don't support multiple Cozmos right now, but the blocks themselves, we update that map dynamically. So it is set up to be constantly messed with. So if he sees a block and knows it isn't there, then he'll dirty his own map effectively and be like, oh, this thing isn't there. But he doesn't necessarily immediately remove that block, because you could have just put like a block, some sort of vision blocker in front of him. As our vision programmer likes to say, the absence of evidence is not the evidence of absence in a strict computer vision sense of the word. So we don't immediately remove the block at that point, but we do dirty it, so it's like, hey, there might be something weird about this. And also, since the cubes have accelerometers on them, we can tell if they've moved when Cozmo's not even looking at them. So in addition to him updating his own sim, he also will try and keep updated if he's not. You can sort of inch them along if you think you can defeat an accelerometer, but most children do not have that level of coordination. Our QA department definitely does, but.
Definitely. And it seemed like you were looking at kind of like static map algorithms. Have you been looking at any algorithms that are more kind of just looking right in front of you algorithms? Like, like I just have this thing right in front of me and I don't want to collide with it. Something along those lines.
So Cozmo only has a single camera, so he doesn't have much depth perception to his camera right now at all. But yeah, like we're definitely looking to improve the pathfinding. It's pretty block dependent right now.
Okay, and I was also wondering kind of, so I know that you use Maya for the animation pipeline. What did you use, and maybe this is just built in, what did you use to do kind of like the physics simulation and stuff like that on the simulation side?
On the
Like any collision detection or anything like that?
Well, we are doing our simulations in Weebots, which
Weebots.
is the robotic simulation software.
Gotcha.
Yeah.
Okay, excellent. All right, thanks a lot.
So in Maya, did you do things that are physically based, like having gravity and stuff like that, so that the animators could do things like the writing itself animation?
Well, no physics per se, so we just export the animation from robot, but in Maya, sort of animators can see if the robot is like on the plane and such. And so sometimes we have like placeholders for cubes and things like that, so that animators can work with other objects. But no like physics simulation in Maya.
Awesome. Well, thanks everybody. We'll be around. Yeah.